All right, so today we're going to be looking at lesson 13.1. We're going to be looking at angle relationships in triangles. So they first start off by telling us that the design of the Rock and Roll Hall of Fame in Cleveland, Ohio includes triangles. As you can see right here, we have a bunch of triangles that are made of glass, and some of them need to be replaced. So to cut the glass correctly, we need to measure some of the angles of the triangles. Jason owns a glass company, and he is going to be cutting the glass for the repairs. One of the tools he's going to be using is called the parallel postulate. So I realize a glass company doesn't have in their toolbox the parallel postulate. They're going to be using other methods, but they're trying to relate this concept to real life. And so this is as close as they can seem to get it. We're going to be using the parallel postulate. So he can't remember the sum of the measures of the angles of the triangle. And so he is going to begin by drawing one of the triangles that he needs to replace. So what you want to do first is to draw this triangle on your patty paper. You could also just take a piece of paper and create a triangle, and it would work the same way. So that's what we're going to start by doing. So I'm going to take my patty paper, and then I'm going to trace this triangle. And you don't need to flip it over and trace the back. And then it says to tear off each corner of your triangle. So first thing you need to do, actually tear out your triangle. You could use scissors if you wanted. That would be fine. So there's one of my angles. And there's the other. And there's the third one. And then it wants you to arrange the corners so that they are adjacent. So adjacent. Adjacent means that they share a side and they have a common vertex. So if I put angle 1 and 2 such that they are adjacent, it's going to be, let's see, something like that. And then if I take angle 3 and put it adjacent, it's going to look something like that. And so it may be somewhat difficult to see exactly what is going on there. And so I am going to actually cut out my triangle. And so there's one. I'm going to use the actual angles. There's another one to make it a little bit more obvious, maybe, what you would see. Because it makes it difficult when you've got all those pieces that are overlapping. So maybe you see something now. Maybe not. And so what I'm going to do is actually take a piece of paper, and then I'm going to just cut out a triangle. So here is a triangle. It doesn't matter which size you make. You just need to make some kind of triangle. And then I'm going to just cut it. Actually, I'll tear it because that's what they said to do in the book. So tear each of your vertices off. And so one of my vertices was here, one of them was here, and one of them was here. And if I put them together, it ends up creating a figure like that. which it creates, hopefully you're seeing it maybe, a line here. It creates a straight angle. So that's what they're wanting you to see there. So then it says that we are going to write a conjecture, and it's going to be called the triangle sum theorem. So the sum of the measures of the angles of a triangle we made a straight line with them. A straight line has a measure of 180 degrees. So when you take your three angles and you add them together, you are going to result with 180 degrees. So the sum of the measures of the angles of your triangle is 180 degrees. That is the triangle sum theorem. So one challenge you could try is to find a triangle whose corners do not add up to 180 degrees. See if you could draw one. I'm just going to tell you as a hint, it can't happen. It will not ever happen. But if you're not sure, just try. Try and draw triangles, cut them out, move the corners, and check and see what you think. Looking now at the next part. We just made this conjecture about the sum of the measures of the angles of a triangle, and now we want to actually prove it. So Jason wants to prove this relationship to be 100% certain about his information. So the book tells us when we are given a figure for a proof, you can't change anything in the figure. So I can't reorder the numbers that they give me or the vertices or anything like that. But I can add information to it. So we are going to be using specifically today an auxiliary line. That's just going to be a line that we are adding to the figure. So they want the auxiliary line to intersect point A and be parallel to BC. So we want it to be parallel to BC, and we want it to be going through point A. I left off my little arrow there. I'll just pull it back up here. So that's what we want our line to look like. How do I know exactly where I need to draw line D as they labeled it? How do I know that that's what it needs to look like and it doesn't need to be at a different angle, let's say? And the reasoning is the parallel postulate, which they actually tell us is right here. Your parallel postulate states that any point that is not on a line, there's going to be exactly one line that can be drawn parallel to that line. So we talked about that several activities back. If I have a parallel line, or just a random line, and I want to draw a line that is parallel to that given line, there is only one line that's going to go through this given point that is going to be parallel to the given line. And that is the parallel postulate. So that's how we know where exactly line D could be drawn. So some things to think about before we go to our proof in just a moment. If we have these parallel lines, what kind of angles are formed? When we add this line, we have a transversal. We have another transversal over here. What are some lines, some angle pairs that are formed by those lines? If you have parallel lines, you can look at your angle pairs. So we have alternate interior angles, and we actually have two pairs of alternate interior angles. And so we're going to want to be using those, as well as angles 5, 1, and 4 are creating a straight line. And so they are going to all add up to equal 180 degrees. So that leads us to this proof. We are wanting to prove the triangle sum theorem. So that means that the triangle sum theorem is not going to show up anywhere in our proof. So on this proof, if I were giving it to you myself, I would have actually put statement 1 that said triangle ABC with the given angles of angle 1, angle 2, angle 3, angle 4, and angle 5 as my given. And then I would have gone to this step that they actually said is statement 1. So that's just a personal, because otherwise we're actually not going to end up having a given. But if you work through it as the book says, then you don't have a given. So just for keeping with what we talked about usually starting with your given, we're going to make a step 1 where we have a given. So it says through point A, draw AD so that AD is parallel to BC. So I'm just going to drag my line so that I know that they're parallel. And the reason that I can do that is what we just talked about, the parallel postulate. From there, we know that angle 5, 1, and 4 equal 180 degrees by the angle addition postulate. So some of you may want to say, wait, shouldn't that just be the definition of a straight angle or definition of a line? But what the definition of a straight angle says is that measure, and we don't even have, I'll put point E here, that the measure of angles DAE equals 180 degrees. Not that 3 angles together are 180 degrees. So that's why we wouldn't want to put definition of a straight angle or definition of a line for that reason. So for step 3, they say if you have parallel lines, your alternate interior angles are congruent. I personally would have called this the alternate interior angles theorem. But they actually decided to write it out, and that's perfectly acceptable. So because of alternate interior angles being congruent, we know we have our parallel lines and we have a transversal. And so this angle is congruent to this angle. So I know that angle 5 is congruent to angle 2. I have another transversal, which has another pair of alternate interior angles, which means that angle 4 is congruent to angle 3. And so that is what I can say for step 3. For step 4, using the definition of congruent angles. If I know that my angles are congruent, then I know that the measure of angle 5 is equal to the measure of angle 2. And I know that the measure of angle 4 equals the measure of angle 3. And then by substitution property, if I know 5 equals 2, instead of angle 5, I can say the measure of angle 2 plus the measure of angle 1 plus instead of angle 4, I can say the measure of angle 3 equals 180 degrees. And that is exactly what we were trying to prove. And angles 1, 2, and 3 are the angles in the triangle. And as we see in our proof, angles 1, 2, and 3 do sum to equal 180. So that is one way that you could prove the triangle sum theorem. So now let's look at number 7. In this proof, did we have to draw the auxiliary line D through vertex B or C? Could we have done that instead of just doing vertex A? Could our auxiliary line have gone through the other 2 vertices? Yes, it absolutely could have. So they had D right around our vertex A, and so they had it already set up to do it through vertex A, but our auxiliary line definitely could have gone through the other 2 vertices. We just would have needed to make sure if it had gone through B, that the line was parallel to AC, or if it had gone through C, that the line would have been parallel to AB. So you could have done it through any of the three. You just needed to make sure you had a pair of parallel lines. How could I use the triangle sum theorem to show that the measure of each angle in an equiangular triangle is 60 degrees? So first off, triangle sum theorem says that the measure of angle 1, the measure of angle 2, the measure of angle 3 equal 180. If it is equiangular, that means the measure of angle 1 equals the measure of angle 2 equals the measure of angle 3. They're all three the same. And so by substitution, I can actually say that 3 times the measure of angle 1 would equal 180 degrees. And that's because this one would just be angle 1. Angle 2 is the same as angle 1, so I could make that an angle 1. And then angle 3 is also the same thing as angle 1, so I can make it the angle 1 as well. And so I'd have 1, 2, 3. That's where that 3 comes from. And then if you divide by 3, the measure of angle 1 is equal to 60 degrees. And so that's what they were looking for on that one. For number 9, how can we use the triangle sum theorem to show that the measures of the acute angles of a right triangle are complementary? So this is a right triangle where angle 3 is my right angle. So I'm going to start with my triangle sum theorem. Measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. Angle 3 is 90 degrees though. So I can replace the measure of angle 3 with 90 degrees. And then I can simplify this equation by subtracting 90 from both sides of my equation. And that allows me to get that the measure of angle 1 and the measure of angle 2 equal 90 degrees. So that means that this angle and this angle are complementary because they add up to 90 degrees. Complementary means that they add up to equal 90 degrees. And that's always going to be the case. If you know you have a right triangle, the other two angles have to be complementary. They have to add up to 90 degrees. So now let's look at interior and exterior angles. So first off, interior, inside, exterior, outside. Same with the interior versus the exterior of a building. So an interior angle is going to be formed by two sides of the triangle. So if I have a triangle, here's one side, here's the other, there's the angle that's created. This is interior. For exterior, it is formed by an extension of a side. So I'm going to take one side and extend it. Then you have one side of your triangle and the extended part of the other side. This is an example of an exterior angle. So interior angle versus exterior angle. For a remote interior angle, it is going to be an angle that is not adjacent to a given exterior angle. So if I have my exterior angle here in green, this angle here and this angle here are remote interior angles because they are not next to the exterior angle. This is the angle right here that is adjacent to it because it shares that vertex and this side. Some of you may feel like they share this side here, so this angle is considered to be adjacent, but the reason it's not adjacent is because they don't share the vertex. One of them is at this vertex and the other one is at this vertex. So yes, they do kind of share that side, but they're not sharing the vertex and the side. So that's why they are not considered adjacent. So let's look at number 10. I want you to see, you can figure out, are they interior, exterior, or remote interior angles? So when you're looking here, it can help by labeling the exterior angle first. So if you look, the one that is exterior is angle 4. So angle 4 is exterior. Then the one right next to that is an interior angle, the one that is sharing the vertex. So that means that angle 3 is an interior angle. Which means that the other two interior angles that are left have to be the remote interior angle. So angle 2 and angle 1 are both remote interior angles. So now we're going to use a protractor to measure angles 1, 2, and 4. So when you're looking here, you want to make sure, if we're going to start measuring angle 1, that you line up your protractor line and your vertex. And then we are measuring the part over here. So I need to start with the 0 over here. This is the 180, so I'm not using these outside numbers. I'm going to be using the inside numbers, and I'm going to get 85 degrees for the measure of angle 1. So if you got 95, that means that you used the wrong set of numbers for that. Now looking at angle 2. We are going to be using the inside numbers again because this is the angle we're measuring. And so 0 starts right here on the inside, on this side. And if you look, that is at 40, 41, 42, 43 is where it ends up. And yes, we do want to be that specific on these. And the reason is because what's going to happen in the next step, number 12. So if you said 45, you were probably really close, but we are going to use the specific angle of measure 43. And then let's look at angle 4. So we're measuring this angle here. So we're again going to start with 0 and go around. And it is an obtuse angle, so we end up getting an obtuse measure. And so if you look, 120, 125, 26, 27, 28, 128 degrees for that angle. So when it says use the protractor, we're going to measure them to be angle 1 is 85 degrees. The measure of angle 2 is 43 degrees. The measure of angle 4 is 128. And so it wants you to try and find what you see, a pattern, something about the measure of the exterior angle in relation to the two remote interior angles. So what do you notice about this one compared to these two? And it says specifically the measures of them, the measures of the two. And it wants us to write the conjecture for it. And so what they are hoping that you will discover is that the measure of an exterior angle of a triangle is equal to the sum of the measures of its two remote interior angles. So that's what they are hoping that you will see. And if you didn't see that, it's okay. You can just begin to learn that that is the exterior angle theorem. Your remote interior angles are always going to equal the exterior angle. So now we're going to actually prove this. And again, we are proving the exterior angle theorem, so that is not going to be anywhere in the proof. So they start by telling us the triangle with an exterior angle of angle 4. And that is our given information. Using the triangle sum theorem. So we just proved this. That means we are allowed to use it now because we're not trying to prove the triangle sum theorem. So our three angles in our triangle, angle 1, angle 2, and angle 3 are going to add up to equal 180 degrees. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. Then measure of angle 3 and 4 add up to 180. Those are a linear pair. And so by the linear pair theorem, we know that those angles have to equal 180. So I would accept definition of supplementary there, although the linear pair theorem is a better reason. But if you put definition of supplementary, I would accept that there. So now looking at step 4, we are actually going to skip how they did it exactly. So we're only going to have 5 steps, but I'm just going to write it in the boxes for 5 and 6. If you see, these both equal 180 degrees. So I can actually say that the measure of angle 3 plus the measure of angle 4 is going to equal the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. And that's because this and this equals 180 degrees. So the reasoning here is by the substitution property. Then, if we use the subtraction property, of equality, we can subtract the common term on both sides, which is the measure of angle 3. And so if we subtract it, we are left with that the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2, which is exactly what they were wanting us to prove. So now let's look at an example of actually using the exterior angle theorem. So they give us a figure and they tell us the measure of angle 2 is 3 times the measure of angle 1. So that means that we can write this equation. Measure of angle 2 equals 3 times the measure of angle 1. We also know from the figure that angle measure of 124 is an exterior angle, and angle 1 and angle 2 are remote interior angles. So the measure of angle 1 plus the measure of angle 2 would have to equal 124 degrees. So then we can use substitution. If we know this equation here, we can replace the measure of angle 2 with 3 times the measure of angle 1, and then add like terms and solve for the measure of angle 1. And then if you know that they add up to 124, 31 plus the measure of angle 2 equals 124, you can solve for the measure of angle 3. You could also use the triangle sum theorem. So in the triangle sum theorem, you could solve for the measure of angle 3. So we're going to actually work through one here. So if you think you've got it, go ahead and pause the video and try and work this one out and then see if you got it right. So I know that 138 degrees is going to equal the measure of angle 1 and 2. So I can say the measure of angle 1 plus the measure of angle 2 equals 138 degrees. Then they told me that the measure of angle 1 was 11x minus 11, and the measure of angle 2 was 10x plus 2. If I combine my terms, I get 21x minus 9 equals 138. And so 21x is going to equal 147, which means that x is going to equal 7. If I substitute into the equations that they gave me, measure of angle 1 is going to equal 11 times 7 minus 11, which is 77, minus 11, which is 66 degrees. For the measure of angle 2, 10 times 7 plus 2 is going to be 70 plus 2, which is 72 degrees. And then we could add those two together, plus the measure of angle 3 equals to 180, or these two angles here are a linear pair. So the measure of angle 3 plus 138 is going to equal 180 degrees. And that means that the measure of angle 3 is going to have to be 42 degrees. So that's how you can actually apply both of those equations that we've looked at today. So now let's look at number 14. In an equiangular triangle, are all of the measures of the exterior angles of the triangle equal? So equiangular means that all of the angles are 60 degrees. And so yes, all of the exterior angles are going to equal 120 degrees. If I extend any of the sides here, this angle is an exterior angle, and it's the sum of this angle plus that one. So this angle is 120 degrees because these two remote interior angles are each 60 degrees. This is an exterior angle that also measures 120 degrees because its two remote interior angles equal 60, and so 60 plus 60 is 120. And by the same idea, this exterior angle is going to equal 120 degrees. For number 15, is it possible for the measure of an exterior angle to be equal to the measure of a remote interior angle? And so what is important? A remote interior angle. They mean one remote interior angle. So if I make up some random triangle, measure of angle 1 and the measure of angle 2 equals the measure of angle 4 as the exterior angle. If angle 2 and angle 4 are the same thing, that leaves measure of angle 1 to have to be equal to 0 degrees. However, we can't have an angle that is 0 degrees and still have a triangle. 0 degrees would be just a straight line, which is also 180 degrees. So it doesn't work. So is it possible? No, absolutely not. For number 16, if you have two angles of a triangle that are equal to the measure of two angles of another triangle, what do we know about the third pair of angles? The measures of those third angles are going to have to be congruent. They're going to have to be equal. If we know this angle and this angle, this third pair of angles is going to have to be congruent. So now, let's look at some of the homework questions. They ask us to find the measure of angle 1. We know that the measure of angle 1 plus 90 degrees equals 125 degrees. And so if you subtract, you end up getting 35 degrees for the measure of angle 1. For the measure of angle 2, we know that the measure of angle 2 plus 125 degrees is going to equal 180. And so that's going to give that the measure of angle 2 is 55 degrees. So number 19, it's trying to get you to do it without a figure. If you need a figure, go ahead and draw it. That's fine. It tells you your two remote interior angles measure 37 and 62. So the exterior angle would be the sum of those. So 37 and 62 is going to add up to 99 degrees. Then the third angle in the triangle. We know that 37 plus 62 plus, I'm going to label it as T for the third angle, equals 180 degrees. And so if you solve for that third angle, you're going to get that it equals 81 degrees. So now looking at this last figure, they asked us to find a bunch of different angles. First thing you're going to want to do, you have a triangle, so we know that those three have to add up to equal 180 degrees. So I'm going to set up an equation. 2x plus 2 plus x plus 4 plus x equals 180. So if I combine like terms, I have 4x plus 6 equals 180. Subtracting 6 gives me 4x equals 174. And then dividing by 4 produces x equals 43.5, which is fine to get a decimal. It's just, you probably wanted to double guess yourself whenever you got that. So now, we know angle A is 2x plus 2. So for the measure of angle A, we can plug in 43.5 into that expression, which is going to produce 87 plus 2, which is 89. So the measure of angle A is 89 degrees. Then, for the measure of angle C, we know that it is x plus 4. So 43.5 plus 4 is going to produce 47.5 degrees. So angle C is 47.5 degrees. For angle A, B, C, it is just x. So we have 43.5. So that angle is going to be 43.5 degrees. Then for angle A, B, D, we know that the measure of angle A, B, D is going to equal, there are a couple of ways you could do it, but it's going to equal either 180 degrees minus 43.5 degrees, or it equals the measure of angle A plus the measure of angle C. Either way, you should get 136.5 degrees. So on these, there are multiple different ways that you can work through them, but hopefully this helps you with understanding some of your angle relationships in your triangles.